Hang on, give me a minute, and we can start. There we go. Where's that clicker? Here it is. Okay. Actually, this is the presentation I made on Sunday. Okay. Have you started, David? Mm-hmm. Okay. Well, this is the final presentation for NPA 19, and to be honest with you, I was planning to give a fancy presentation and get it all put together, but I didn't have time to do it. But that's okay, because I think this will actually be better, because what I want to do is just sort of share stuff with you and just give you sort of a stream of consciousness of some of the things I'm currently working on, and as it relates to the paper, this is the work that I am most excited about. My thoughts are running at about...
Not fair.
My thoughts are running in about 16 different directions, but if there was one direction that I had to choose as the one that I'm just passionate about, it's what I'm going to be talking about today. So that is structure. And Dr. Lucas said earlier, mentioned that the Greeks said those who don't know geometry are not allowed in here. And I think that pretty much leaves out all of mainstream. And so the cool thing is people like Don Briddell and Bill Hohenberger and Stoyan Sarg and Vladimir Ginsburg and of course Common Sense Science, we're the only ones that were in and everybody else is out. So that's my passion. I love the idea that there's so little competition out there. There's not very many people who are actually trying to figure out the structure of atoms. And so I got a good chance, of being the one that figures it out, or at least part of it. So that's exciting. I mean, I feel like there's a chance that we could actually get this thing figured out. And so what I'm going to be talking about today is rather than try to propose a model and say this is the model, I want to find a tool so that I can take any model and say, how does this model work? And to me, that's more valuable. So I can then say, let's take a look at Don Briddell's model. Let's take a look at, Bill Hohenberger's model or whoever else's model and test it, according to a certain set of rules. Now, when I asked Don Briddell, and this is why I put these slides up here. Here's some possible models for particles. And I went through this 3 days ago, but for those of you that weren't here, whoops, I went the wrong way. It could be a toroid. It could be loops like these, interlocking rings, with just more or less rings. Those are possibilities. It could be rings like these, and I forgot to bring them up. I've got some ring. Those are my favorite rings that we use for the Senyek Award, and the Borromean rings, which are actually two different structures. That's a possibility. The toroid model, which Bob DeHilster helped to build, which has these laser lights going around like Christmas trees while the whole thing is spinning around. You get a quantized effect. And I know that I've demonstrated this numerous times before, but for those of you that don't know, I brought some toys along. Hang on, let me move over here. I know this is not new. This is something I've shown people before, but I'd like to show it because it's important. The idea, I believe, this concept is called the strobe effect. And the strobe effect is the idea that when for example, you are seeing a roulette wheel spinning around and it seems like it's moving backwards and then all of a sudden it starts moving forward. What's happening is you're getting a frequency of the light, 60 hertz, mixing with the frequency of the rotation of the wheel. And when they're in lock, then you're going to get it looking like it's standing still. And then when the wheel slows down, it looks like it's going backwards. And then all of a sudden, there's a quantum change, and it looks like it's going forward. That's called the strobe effect. It's the same thing we see in this little ball right here, which I'll show you. Have this thing spinning around while the lights are turning on and off. And, oh, come on. The lights won't come on. No, the batteries aren't dead, but sometimes they'll start. Oh, for crying out loud. Well, okay, you've seen toys like this before. The idea is that the lights are turning on at a certain frequency, the thing is spinning around at a certain frequency, and so you might see it standing still, and then you'll see it going backwards, and then you'll see it leap somewhere else. That's the strobe effect. It's the same thing also like with the wagon wheel. The wagon wheel looks like it's standing still, and then it's going backwards, and then all of a sudden it's going forward very fast. That's because there's a frequency of the frame rate interacting with the actual frequency of the wheel. Every time there's interaction of two frequencies, and I'm maintaining that that is not just a fun little optical thing, that is fundamentally how particles work. And it is a necessary consequence of the fact that we live in 3D. So when you look at this model, what I see is could be charge. And by the way, Don Briddell doesn't see charge, he sees ether or energy, I don't know what he sees. And Bill Hohenberger sees ether. I don't care how you look at it. One thing that we all agree on is something is circulating around in these circuits in order to cause these things to come into balance and to exist. And so whatever you want to do, but whatever that thing is, it's got to obey certain equations. It's got to obey certain laws that we agree on. And I've asked this very question to Don and Bill. Okay, so it's not charge. Whatever you want it to be, is it going to obey these laws of electrodynamics? Is it going to obey that? And they say, yeah, it does obey those laws. So I don't care what you call it, as long as we agree on that much. Because then we can start getting real about it and start applying some mathematics to it. But getting back to this model, what I visualize is the fact that we live in 3D. Every circuit is going, however path it goes, it's going to have a cross section. And the fundamental notion is that the reason why we need these circuits is because it is the motion itself that causes it to bind together. Okay, I guess I need to take a little detour and explain exactly why that is. I call this Ampere's principle, not Ampere's law, because when I say Ampere's law, then you're thinking of a particular equation and you're not seeing the bigger picture. When I say Ampere's principle, what I mean is the principle that when matter flows through a cross section and then you decrease the cross section, that the velocity has to increase because the same amount of matter has to pass through adjacent cross sections. We see it when we put our finger over a garden hose. We see it when the water flows down and the shower curtain goes in. That's called the Bernoulli principle. Or when you blow air over a straw and the water comes up. It's the same thing. It's always the same thing. What is causing the attraction? The attraction is coming from the motion. So either the pinch is causing the increased motion or the increased motion is causing the pinch. Either way you look at it, those two things are inseparable. And the fact that you have a spatial consequence, which is the pinch, connected with a time consequence, which is the increased motion, that's Ampere's principle. I call it the principle of translation. By the way, there's only one other dynamic principle, and that's what I call Faraday's principle. Faraday's principle also takes a spatial thing and connects it with a temporal or time thing. But in this case, it's rotation. When something rotates, you always, inseparable, have a shear. Okay, think about it. If you're standing on a merry-go-round, the guy closer in is moving at a slower velocity than the guy further out. Okay? And so there is a shear there. And likewise, if something has got shear, then ultimately there's some sort of a rotation. It's part of a circuit. So you can't separate those two ideas. That's Faraday's principle, which is different than Faraday's law, because I don't want you to be limited or get all hung up on, the form of the equation or, whether it's right or wrong or that. That principle is a principle of nature, and I'm submitting that those are the only two principles of dynamics that we need. And from that we can derive wave equations, we can derive everything else. Those are the things, and both of them have a spatial idea connected with a temporal idea. Anyway, I got way off track. What I'm getting at here is with the principle of this spatial idea, this pinch effect, it is the pinch effect that causes particles to stay together, okay, or anything to stay together, and therefore we must have motion in order for things to exist at all. That's why there has to be motion inside. If I've got an object and I say this thing is held together, what's holding it together? It's its own motion. There must be motion inside it. And not only that, because it's finite, eventually that motion has got to come back into itself. It has to be a circuit. And that's where there's pretty darn good agreement among us in the NPA about this idea, that circuits are what it is. Common sense science, Don Briddell, Bill Lucas, Bill Hohenberger, all these various models, they all have that in common. They all agree that we need circuits in order to be able to understand this. So what I want to do, and my passion, is I want to understand how to analyze all circuits and see if I can apply and determine their fields and determine the electrodynamics and figure out where they go next. Then I don't care what it is, I've got a tool to do that. And I believe that's what I have. I have, what I've done, this paper has done, is I've found no matter how complicated the circuit you give me, I can give you a series of ellipses that corresponds to that circuit, and I can add up those ellipses. Now I can't necessarily figure out Don Briddell's complicated thing, but I can figure out the equations of an ellipse, and I can add up all the fields, and then I can do this. In other words, I determine the fields of all these various rings and add them up spatially, and then I take the square of them because the energy is the square. So in other words, it's not the sum of the squares, it's the square of the sums, and that's very important to make the distinction. Because when you, in other words, I'm not adding chunks together, I'm adding all the elements of the contributions and then squaring them and adding the chunks. And that's very important. And this process is going to allow me to do that for any circuit. It's a tremendous amount of calculations for whatever, but what I want to do is put together a numerical method to analyze any possible circuit, and that way, lo and behold, then I can calculate the dynamics and let it go. So that's my passion. I'm not going to bore you with the mathematics, but essentially, the idea is this: if I have my arbitrary path, I can determine that path in terms of some parameter, and I'll normalize it so that it goes from 0 to 2 pi. I can do that in anything. So I start here, call that 0, and I go around, and then whatever, and I end up here. That's 2 pi when I get back down, and then I can just follow that parameter. Then what I can do is take that thing and put it in the x, just find the x component of that, and that's going to be a periodic signal in terms of that same parameter, right? And it's going to eventually start repeating. Now that, we know, I can decompose into a Fourier series. I can do the same with the y component, and I can do the same with the z component. Okay? Now, here's the trick. What I'm going to do is I'm going to take each component, say the first harmonic, and add the first harmonic of the x, the first harmonic of the y, the first harmonic of the z. So they're all periodic in the same, to the same frequency. And I add those together. So what I have on the x-axis, if you can imagine, is just some magnitude times the cosine of theta plus some phase factor. So I'm going to have I have a magnitude and a phase factor for each of the components. So I've got 6 total things. I can convert those 6 things. It turns out I can show you, and this is what I show in the paper, is that I can turn that into an ellipse. So what I have is an ellipse in the first harmonic, another ellipse going in some other direction in the second harmonic. In other words, it goes around twice during that period, and another ellipse over here that goes around 3 times, and I can just keep adding these all up, and then I can get the decomposed thing. So I wanted to show you an example. Here's Don Briddell's structure, and they're not nearly as beautiful as his. I made this myself. But what I'd like you to look at, if you can see it, is the white. Can you see the white? All of you? Do you see it from this point of view? You should see one ellipse, kind of up and down. Do you see one ellipse? But if you look at it from this point of view, you should see 2. You see 2? Everybody, is it big enough for you to see? So it's going around twice. You should see like an 8 from this, but from this it looks like a 0. You see what I mean? It's the same shape. So what I'm saying is that I would expect to see a first harmonic in this direction. I would expect to see a second harmonic in that direction, and there might be third and higher harmonics. But that may be all. That may be sufficient to describe this form. So here's the goal. What if I can find a mathematical formulation for this shape, for example? Then I can decompose it into its harmonics, and then I can analyze the harmonics, and I can then, like I said, let it go. And in fact, that's what I did. I'd like to show you. I'll get out of this. I just got some neat stuff that I put together with Mathematica, and I can't remember which file is which, but I think I got lucky and got the right one. No, I didn't. Hang on. Oh yeah, this is it, but something happened. I'm sorry, and I can't. Why is it acting this way? Oh, for well, that was supposed to be Don Briddell's thing, but something really goofy just happened there, and I can't get to it. Huh. Well, I'm sorry. I don't want to waste time. Darn. Okay. Well, okay. That was supposed to be done. I actually did figure it out, and it's, for some strange reason, it's not displaying correctly right now. But the idea was I wanted to just show you that I did actually describe this structure mathematically, so now I can do that analysis. So that's what I want to do. But I want to now talk about what would qualify as a possible structure. Okay, in order to actually qualify as a real model of a real living, or not living, but actual atom, it's got to meet some very, very rigid requirements, and I'd like to talk about them. This is a really neat thing, but it has one real serious flaw, and that is, remember I said earlier about the cross-section, that there has to be circulation around the cross-section or the cross-sections would fly apart from each other. There's no motion to keep them together. There's no suction to keep them in. There has to be internal motion inside even just the white one alone. It's not just an infinitesimally thin thing. It's got thickness. And Don, I mean, he's a great guy, but he hasn't taken that into account. So what I want to do is just simply look at one loop all by itself and see if I can come up with a structure that actually has 3 dimensions. And it's not good enough to say, all right, I've got a sheath on the outside and then I've got another one inside and another one inside. That's not good enough because the ones on the inside have a different path length than the ones on the outside. Does that make sense? And that's not okay, because then I've got 2 frequencies and they're rubbing against each other. Besides, 2 elements on the outside sheath are not moving relative to each other, and that's not acceptable. Okay, everything has to be moving relative to something else, its neighbors, or they'll fly apart from each other. So there has to be shears everywhere throughout the whole structure. So I've been thinking about this for quite a long time. What's the way to make that happen? And I know I've shown this model to several people before, but this actually does do that. Okay, this is three simple rings that are wound around each other that do that. Okay, that in other words, there's a shear that each one is moving relative to each other, even along the cross sections. They're actually kind of going like this as they're going down the structure, and that's not good enough either, because these have thickness. I've got to have structure within each of the 3 elements. You follow what I'm saying? Because I can't just have this be a finite thing. It's got to be something with structure in and of itself. So can I take, here's another possibility. Instead of having 3 rings, I could have, say, 10 rings, or 100 rings, or 1,000,000 rings, or an infinite number of rings, just all wound up like this. That's not good enough either, because then they're all going to be lying on the surface. And let me show you, if Mathematica hasn't messed up with me, I'll show you what I mean. Let's see. Okay, I think it's down here. There we go. This is something, this would be what I'm talking about. This is a whole lot of rings together, but they're all on the surface. So I have even if I have an infinite number of them, every single one of these is lying on the surface, and it's an infinitely thin surface, and that's not real. So I've got to have a structure that goes into the surface and comes back out again. You see the challenges that I'm trying to get to. I've got to have something so that everything shears with everything else, and yet it goes into and out of the circuit at the same time. That's the problem I've been trying to solve, and that's what I'm going to propose a possible solution. As far as I know, nobody's even asking this question, but I hope you get what I'm saying. Everything has to shear against everything else. It has to have thickness. It has to be finite. It's got to meet all these conditions to be a viable model. So, my thought is to take each of these and have a fractal-like structure, and a fractal structure would then take each of these individual loops and make that into 3 loops, okay? And then take each of the 3 from that and make that into 3 loops, and I just keep going on down and down, and I get to an infinite number of these loops, all of which are moving in and out of each other, creating a surface which has thickness. You see what I'm saying? That's what I'm after. And so I'm very excited about doing the math on that, and I actually have been working on it for a couple of years now, and it isn't an easy problem. I won't go into the details of why that's a tough problem, but I do believe that there's at least fruit with that. And let me just, now that I've proposed that model, let me tell you what the possible ramifications of it are. Well, first of all, I want to solve a very simple problem first, because if I can solve this problem, the one I'm just describing right now, then I can take it and solve problems where there's more waves. I can take it and solve it problems when, like I'm looking at Don Briddell's thing. I could do anything, but I first got to do this because I got to figure out a way to have a structure that has thickness and solves all these problems. There's one other really beautiful thing about this model, and I want to show you that right now. Each of these, here, this is a good example. Each of these loops now lies on the surface of a donut. Now I want to see, this is a very thick donut. This is 3 rings all lying on the surface of the donut. You kind of have to imagine the donut. But that's just like the 3 rings I'm showing you. And now I'm going to flatten it out. And now it's maybe a little more obvious. Okay, you getting the idea of what this looks like? Now, if I add more rings, the donut will be much more apparent. Let's just try some arbitrary number of rings. And boy, is it slow. Come on. There we go. Now you can see the donut clearly. Okay, and again, they all lie on the surface. They don't go into the surface at all. But that's just the first generation. Got it, thanks. So, but there's something very extraordinary about these rings, and this is important to understand. They're called Villard-Seau circles. For those of you that aren't familiar with that idea, I want to just show you now the circles lying on the ring itself, and it looks like this. Here's the donut, and I'll show it to you from different perspectives. Okay, can you see that the ring is the line that's kind of not with all the rest of them? There's actually two of them there. You see that? Yeah. There's one ring, and there's actually two of them. One's a right-handed ring, and one's a left-handed ring. Okay? And then these Villard-Seau circles, turns out, are exactly the same. If you think of now that the donut has a radius, that is the radius from the center of the donut to the center of the cross-section of the donut, that radius is exactly the same as the radius of the individual rings that are lying on the surface. And here's what those circles look like with the donut missing. There's just a couple of circles. Okay, so what I just said is really important. Let me say it again looking at this. The radius of this whole thing is the same as the radius of the three rings that lie on the surface, because they're just like Villard-Seau circles on the surface of this donut. Okay? And the significance and the really cool thing about it is when I do it to the next generation, those three rings will also be the same radius. And when I do it to the next, they will all be the same radius. And they're all circles. There's absolutely zero torsion. They're all circles all the way down, and yet they're all knotted inside each other. And that's why I think this model is so viable. Let me explain why I think there's several reasons why I think that's important. I visualize this thing as charge, or what I might call a primal charge, circulating around these rings. And they're all circulating in a perfect circle, so there is no torsion at all. That's a real important, that's a key for stability. See, what I'm after when I'm building these models, how do I know if the model is right or not? First of all, it meets all these strict criteria. Second of all, it's stable. When I run this thing and I say, where's it going to go next? It doesn't go anywhere. It stays where it is. That's the test. That's what I'm looking for. Then I know I've got the right thing. So that's kind of what I'm after with this. I think this has a real good shot at doing that because there's no torsion. It's just wanting to go right where the circuit just stays right where it is, and it's totally oblivious to everything around it. So I'm very excited about that possibility, and hopefully maybe in a year from now I'll have something to show you on that. But that's my work in progress with that. Let me explain, I mentioned torsion. Now we all kind of understand the idea of torsion. Torsion is, I like to think of it as a second order torque. A torque would be, sorry about that. A torque would be, you have a force or a movement or whatever. It's going one way and you got another one going the other way. That's a torque. Okay, everybody gets that idea. A torsion is a step above that. If I've got a torque, a twist going this way, and then I got another twist going that way, I can't do it without messing up the mic. It's a torsion, okay? That's actually like a quadrupole moment, okay? And torsion happens when something is turning, but it's also changing the way it's turning. That's called torsion. And there's Robert Keene is one of the guys been active in the NPA, says, well, you know, there's two different kinds of torsion. There's torsion from the actual motion of the curve changing, okay, and that's called Frenet-Serre, for those of you that like math. But then there's a second kind of torsion, and it's called topological torsion, and I have to get my toy, hang on. You see, each one of these circles individually has no torsion. It's just a circle. But collectively, there is torsion. The torsion comes from the combination of the three things. In other words, torsion is either right-handed or left-handed. And we can see, you know, that this collection of circles, if you're going to follow one circuit with your thumb and curl around with your fingers the direction as it's moving around the circuit, you're going to get either right or left-handed. That torsion is called topological torsion, and that's what I'm after. I want a model that is just filled with topological torsion. And so this concept that I'm proposing is all circles that are knotted together in such a way as to create all kinds of topological torsion between each of the circles, which allows the condition for the shear, which is the relative motion between things, to enable them the attraction that's necessary to maintain stability, to occur. So anyway, that's the model. The idea and the tool then with this Fourier concept to actually decompose whatever and be able to just get it down to this basic loop. I'll give you one last example if I can find it, and that's called spherical rotation. Spherical rotation would be, let's see if I can model this. Remember that these are dynamic. These are representing circuits of moving something. You can call it whatever you want. I call it charge. But moving something. But now imagine that these things could also be moving in a second way. They could be spinning this way, spinning around in a circle like this, okay? And that gives you a whole nother possibility, and it turns out that spherical rotation, which I just described, is also known to be stable, and we do see it in nature, and we sometimes see it in tornadoes and things like that. And so I want to show you a picture of it if I can get it here in Mathematica. But everything seems to have got messed up here. So I'm not sure if I can. Hang on. There it is. How about that? I got lucky. This is a picture of spherical torsion. Okay. Now you notice that they all go through the poles. There's actually 3 of them here. There's 3. Here's just one. Okay. One loop, and it's going around. Let me. I guess I need to stop. Imagine it this way. If you are in an airplane and you start at the equator, you go over the top of the North Pole, then you travel around the other side of the Earth, you come back over the South Pole, and you come back to where you started. You think you're moving in a circle, right? You just did a circle. That's how it looks to you. Okay, but now let's step back at the Earth and watch the Earth rotate as it's going. Okay, and you're gonna do that motion in 23 hours and 56 minutes, a sidereal day. And from the outside, the observer is going to see it going up to the North Pole and coming back, but as it comes back to the other side is right where it started, from your perspective. So you're going to see a figure 8, whereas the guy inside is seeing a circle. What I'm trying to get at here is you can actually create knots just by rotating things differently. And that's very much akin to, I can do the same thing here, like with the torsion thing that Bob built. This thing can be moving and going around once, but this thing moves around, let's say, at half the speed, so it takes twice as long for it to go around. Sorry about that. Twice as long for it to go around, so that it will actually go around twice. So it thinks it's going in a circle, but you see it going in a little thing that's spiraling around. So it really, ultimately, what I'm getting at here is the circle is sufficient to describe anything, because number one, I can get all the spirals in it by just rotating it backwards. I can get the spherical rotation by rotating it this way. I can get the ellipse by stretching it out, and then I can get this or whatever I want by just adding up ellipses. So I have the tools now to analyze any possible circuit, and I can ultimately break it down into circles, which I can understand. I have a model that I can create which has the potential which has all the requirements that we need. We need a 3-dimensional object. We need something that has torsion at every point. We need something that has topological torsion. And I believe that's what I have. The only thing I haven't got is all the work done, because it's a tremendously difficult problem. But anyway, I'm just sharing with you kind of my thoughts and where I'm heading right now, and I'd be welcome to entertain some questions if there's any time. Okay, come on up. Oh, I didn't finish with the spherical torsion. Here's just different numbers. That's just different numbers of objects. Go ahead, Jeff.
I want to understand why you need the separate rings to have topological torsion when it could be a continuous thing, and you could have the knots that Briddell has and that from the the same thing. You can stretch one loop. Well, what is the reasoning for it? That's all.
Okay, what I'm saying is, okay, let's, I don't know if you can see this, but he just drew an arbitrary path, which is a knot. And what I'm saying is the flow along this path itself is finite. And that's the issue that I'm trying to get at. I'll find whatever, anything finite has got to have structure within it. That's my point. That's my rule. Okay, so, and if it has to have structure, then there has to be something going on inside of it such that there is motion across the cross section itself. There has to be torsion going on.
Okay.
That's what I'm saying.
Yeah, okay, very good. But if they were all looping through each other, wouldn't they all contract on themselves in this sense, even without the extra particle?
No, again, I'm submitting this that matter does not naturally attract. Matter repels, and my argument is basically this simple: no two things can occupy the same space, and therefore, as things get closer to that possibility, they push each other apart. That's the natural thing for stuff to do, is push itself apart. The motion is the thing that we need to account for, and the way to account for the motion is through this Amperian principle, which is clearly, there's all kinds of evidence for that. I mean, Bernoulli's law, Ampere's pinch, whatever pinch you want to think of, it's always motion induced.
Yeah.
And so I'm saying that's the only cause for attraction.
Yeah.
There is no other. And gravity ultimately is just a result of it's a higher order of structure. And I believe it takes place at the molecular level, just like Dr. Lucas proposes. So.
It's very good. All right.
Okay, thanks.
Do a holder, I can take that. I'll take it later.
Oh, okay. Go ahead.
Greg, I've been working on this problem for about 20 years.
I know.
And I've been working on how do you construct the complete set of elementary particles, how do you get the set to decay and have a different structure for each one. And I have the idea that the loops should not break. I have the idea if the loop breaks, there's something wrong with the model. So, so then the question is, how can I get all these configurations and get them to come apart and decay and react and build up bigger things without breaking a loop?
That was, okay, that's the conundrum that I discovered with this. That's why this is so amazingly important. I remember the night that I thought about this, because I was actually looking at the common sense models and trying to figure out how can I get from state n equals 2, going around twice, versus n equals 3, going around 3 times without untying the knot and retying it. And it drove me nuts. And I realized the answer is because these are dynamic. These are actually moving. So when this stuff, and this is hard to do holding this microphone, but when these loops are moving, okay, and there's torsion, topological torsion within the loops, and then we spin the whole thing, see what I mean? Then we can get an interaction between that rotation of the object with the internal rotation going on there, and that can create quantized changes, and that's when the knots get untied. You understand? It's just like, it changes its state, and when just like that strobe effect, when it goes from when it goes from going around once with a little precession to going around twice without precession, that's the point at which the knot got tied.
Well, my problem, for instance, when I have a model for the neutron and it's got to decay to a proton, an electron, and a neutrino, how do I get 3 entities out of one without breaking any of the loops?
Well, okay, I don't really know what a neutrino is.
What you know about electron and proton?
Sure. Well, I mean, in my view, I guess this is only a guess, but in my view, I think of the electron as being the one that is the sphere, because I think that the 2 rotations together sympathize with each other and actually create less energy. And there's a whole lot of reasons why I think that. I think the proton is probably the toroid. But that's just, that's my intuition. And everything else, in my opinion, is just what I might call different kinds of topological nodes in the electrodynamic field. And when, for example, the particle changes state from, let's say, n equals 3 to n equals 4, we say, it absorbed a photon. Well, there is no such thing as a photon, but there was a node in the electromagnetic field that got absorbed into this rotation process, and that quantum event untied the knot, and at that point we said, it absorbed this particle. Well, there is no particle. It's just a change in state of the rotation. That's how I see it.
Yeah, well, I agree with that part for radiation emission and absorption, but my problem that I've always faced is how do I separate things and put them back together without breaking loops? And,
yeah, there's no need to break loops. Another example is this rotation, this spherical rotation. You know, I basically went from a perfect circle. It looks like a circle, but when you spin the whole object, suddenly it becomes a figure 8. There's a knot in it, and so I didn't put the knot comes in there because the whole thing is rotating with respect to its environment. So that's where the knot comes in. It comes from the motion, and actually it's somewhat a matter of perspective. So, all right, I guess we're done.